Hey, Thomas. Be ready in a few minutes. How are you?
I'm good, thanks.
Hang on a second. I got my audio pretty quiet. Bear with me for a second. So, how are you this morning?
I'm good, thank you.
Good.
How are you?
Not bad. Not bad. Not bad. I'll be ready to go in about 5 minutes or so, okay?
Okay.
All right. All right. Please stand up. Hey, Thomas, while I'm getting going, and we have like 3 minutes. If there's anything you want to ask me about, feel free to do so. I'm just going to be writing some stuff on the whiteboard.
I'm good for now, thank you.
Okay, Thomas, good. Okay, we'll get going in just a few seconds. So hang in there for just a minute. All right, well, good morning. So what we're going to do today is keep finishing off the chapter 2 material. We're basically almost done, but have a little bit more to do with that. And then just give you an introduction to what's called Bernoulli's equation, which is one of the most important ideas in fluid mechanics. So at partway through, we're going to take a break and do a practice quiz. And but please don't stress about it. It's purely a practice quiz just to see if we're set for Thursday. And I will stop at some point and see if there's anything you guys want to discuss about Thursday. But for right now, let's go ahead and get going, finishing off on chapter 2, where we ended up last time. Was we were taking a look at what's sometimes called Archimedes' principle, okay, or ideas about buoyancy. And we came up with an equation that gives us the buoyant force on an object in a fluid, and like to add a couple things to it. So the first thing I'd like to do is be able to answer that question. If we have some object and it's submerged in a fluid, like this object right here, imagine it's a submarine or something like that in water. It doesn't need to be in water. Hey, is it going to rise or sink? Well, what I would like you to be able to do is do a quick free body diagram of that object. So remember, when you do a free body diagram, what you're doing is isolating the body. You're imagining, like if I were doing a free body diagram of this eraser right here like this. Well, yes, I'm holding it, okay? And maybe there's something else that could be going on. Like, so maybe like it could be resting on a flat surface and maybe something's pressing down on it. But we try to do a drawing where we imagine it's just sitting there, just isolated, and draw all forces acting on it. So with no further comment, why don't you go ahead and try to do a free body diagram of this object where this ellipse right here represents that object there. See if you can get all the forces acting on that object. Okay, hopefully you got started. In this particular case, we can get it down to two forces. We can get it down to two forces. Okay, well, first of all, we're going to be assuming that this object is on Earth, okay? And so one of the forces would be weight. So I can write that down. There would be a force down, which would be equal to its weight. Okay, and then in addition, someone might start drawing a bunch of different pressure forces. Pressure force this way over here, pressure force in over to the left, okay, pressure force up from below, pressure force down from below. What do I mean by pressure force? Pressure force of this fluid over here. But what we did last time is we found that we can, for a submerged object, we can break it down into just a single force that we call the buoyant force. So that would be called the buoyant force. Okay, so there's a good free body diagram of an object that is buoyed or supported by a fluid. And is it going to rise or sink? So is this object right here, is it going to sink down or is it going to rise up to the top? Well, obviously it's going to involve a comparison between these two numbers right here. If the weight is 100 pounds and the buoyant force is 200 pounds, it's going to go up. Okay, well, we can be a little bit more detailed than that if we can write expressions for these two objects right here in terms of symbols that are on the board. So let me give you a second and see if you can write those, think about different equations we have and write expressions for those two things. Okay, I'll give one of them. We found that the equation for the buoyant force of an object in a fluid or an object supported by a fluid is rho Vg. And I've left a little space here between the rho and the V and the G because I'm going to do a couple subscripts there like that. All right. And so let me, if you got it, great. Try to keep going. And if not, see if you can get a little bit more, or feel free to ask me questions at this point. All right, so the this is a good equation. Like if I were to see this on your quiz on Thursday and you carried out the computations using this expression correctly, hey, full credit. But we want to be precise here because if you take a look at this picture, we have two different densities. We have the density of the object and we have the density of the fluid. So what density do we want here for the buoyant force? It's going to be the density of the fluid. So I'll just do rho sub F for the fluid. Okay, how about V? What V are we talking about? Well, you don't see this in the book necessarily, but on the board last time I said it was the volume that's actually submerged, okay? And in some cases we can have objects that are partially submerged. All right, so it's not crucial that you have this in your notes, but it's important that you understand this. Okay, how about the weight of the object? Well, we could do mass times gravity, but it's helpful to note basically that if I'll just write that up here, the weight of the object would be mass times gravity, okay? But in terms of the symbols on the board, we don't have density, we don't have mass. We know density of an object is a ratio of its mass to volume. So we could get the mass of the object by doing the density of the volume. All right, so that is a good free body diagram. And then what I wanted to keep going on it was come up with a criteria for floating or rising. So what if something's going to rise? Okay. Well, what we said is this buoyant force here is greater than this weight force right here. Okay. So it's going to rise basically if we could write an expression. It's going to rise if this buoyant force, okay, is greater than the weight. Okay, and so that would be basically, you don't need to write this down as like a rule or anything like that. This is more an understanding exercise. There's a good expression that says, hey, if I have an object that's submerged in a fluid, it's going to rise if this is true. And I'd like you to think about simplifying it and what actually that would say. So one more step and we're done with this part of the discussion. Okay, well, let's do a comparison. Clearly, we could cross out the G's. The G's aren't supposed to be determining what's going on. And in this case, I said we're imagining this object is submerged. So this would be the volume submerged, and this is the actual volume of the object. Those are going to be the same. So it's going to simplify that it's going to rise, okay, if the density of the fluid, get that, pardon me for just a second. It's going to rise if the density of the fluid is greater than the density of the object. And that's probably something that you guys already know. If we put an object in a fluid, if it is less dense than the fluid, then it's going to rise. And if it is more dense than the fluid, then it's going to sink. And that just comes directly from these principles that we actually developed. Okay, good. So that's a little bit more on buoyancy. One more thing on buoyancy before we move on to the next topic. I'm just going to, no need to write this next thing down, but I would like you to critique what I did yesterday. If there are any questions out there, please go ahead and speak up.
I was about to ask you before you erased it. Can you, when you're talking about buoyancy, can you always assume that the weight will be density times Vg?
Yep. So the weight of an object is going to be its density times the object's volume times gravity, and that's just equivalent to this equation right here, mg. Sorry, on the board. That's the expression we use to get the weight of an object. Okay, but many times another way to get the weight of an object is just to do density times volume times gravity.
Okay.
All right. Okay, so this next thing you don't need to copy down, but if I could just take you to yesterday really quickly and just think about it. We started working on manometers. We made some good progress on that, okay? And I had a manometer example, which I finished off on class, okay? And I'd like you to just maybe use your intuition or also think about what we just did. And maybe critique what I did yesterday. So let me give you just a second to think about that really quickly. Okay, so we did a manometer example where we had some water in the manometer, and I imagine there being some mercury poured on top of that. And well, let's just go ahead and compare. Let's just think about that rise or sink idea. And the way that we would do that, when we would compare the density of the mercury to the density of H2O. All right. Okay. And hopefully either from experience or by problem solving, this is a lot denser than water. So what's this stuff going to actually do if you put it on water? It's denser than water. It's actually going to sink. So, hey, my bad on that previous problem, last time. The math that we did was all correct, but what actually would happen in a case like this is the mercury should have sunk. And so I should have actually done something like olive oil instead. And let's just take a break for just a second. You don't need to write anything down, but let me just check that out with you and see if that's right. So, just a quick one that you can do at home just to think about this stuff a little bit. Bear with me for a second. So what I got is I got this jar right here, and I'm just gonna get a little olive oil on the bottom. So I just got like plain old ordinary store olive oil. So put a thin layer in there. I don't want to waste this stuff. Okay, so olive oil is like a lot of different oils, like engine oil. It's pretty viscous stuff. That's kind of an interesting property of olive oil. It has a little bit of resistance to flow, but it's also, compared to water, it's not as dense as water. Usually oils are less dense than water, and you'll notice that for engine oil. And if you do any work with any other oils like that, oils are generally less dense than water. I'm going to adjust the screen for just a second. So, hey, just yourself, let's just do a quick prediction. What if I take some water and pour it on top of that olive oil? I'm going to give it a try. Hopefully I won't make a mess on my computer. I'm going to go back a little bit just so I don't get any water on my computer. Okay. So, just a second ago, it was hard to see. I did it kind of slowly, but the water was actually on top. And pretty quickly, we're getting a separation where actually the oil rose up above. And it's a little bit hard to see because of the tint, but if I could get it at the right angle, there you can see we're getting really good separation where the oil all went to the top. And that is this idea that this oil is less dense than the water, so it ends up rising and ends up above there. And I can do a bunch of different things where I can actually get a little bit of swirling going, a little bit of vortex going like that. And very, very quickly, it goes back to that separation where we get olive oil floating on top of the water. And that's actually buoyant effects. Okay, good. Great. All right. One more type of example that you can do. All right. What we did last time. So a quick example on this. So this is more on buoyancy. Okay. So I'll get the example up there in just a second. But let me just get a little bit of a principle up there. So if we imagine like we have some water or something like that, and we put objects in there. Okay, we put some objects in there. If we put an object in there, no need to write this down. I put in an object, and its density, okay, is something like 1,200. Okay, and we're going in SI units, so let's say 1,200 kilograms per meter cubed. Okay. Well, what's that object going to do? Clearly, it's going to sink. All right. All right. What if I put an object in there and its density is, say, 100 kilograms per meter cubed? That sounds like a big number, but that would be something that is really, really almost like a foam or something like that. It doesn't have very much density. Well, clearly that object is going to float. Its density is less than water. Okay, but it gets kind of interesting when you get something like that has density, say, around 800 or something like that. Okay. It's less than water, and so it's going to float, but some of it is actually going to be submerged. And a good question that often get asked is, well, how much is going to be submerged? And let's do an example like that really quickly. So first example of the day. Hopefully you got your calculator out. We'll go ahead and get going. So we're going to imagine a cube, which is 1 meter on a side. So that's our object that we're going to look at. Hopefully you can see that. Let me get a little bit closer for you guys. A cube, 1 meter cubed on 1 meter on a side. Okay. And that cube is made out of a wood, and wood's density is actually generally, well, usually less than water. And so this wood is going to have density 720 kilograms per meter cubed. Okay. So, and what we're going to do is we're going to put that cube in water. And the question I want you guys to work on is, what height, if we put it that way, yeah, what height, or what is the height of wood above water? What height of wood, and I'll just call it the cube, is above water? Okay, so I would encourage you to do a couple drawings, do a free body diagram, and then see if you can write an equation that allows you to solve. Pretty ambiguous, but let's go ahead and let you get going. So once again, you're going to do a drawing of the situation and then do a free body diagram of the cube where you indicate all the forces and see if that can allow you an equation to solve. All right, let you guys work on that for just a second. I'll slowly get through it. This is work time, so if you want to unmute and get a question out there, please go for it. I'm going to make the cube a different color just to help out a little. All right, I'm going to start talking in a minute, but that is a good start to the problem. Okay, this object is less dense than water, so it should rise and float, but it's not going to actually come out of the water, so it's going to be sitting in the water somewhat. And I've got some portion of it here sticking out, all right? And that's what I'm trying to solve for. On the free body diagram, there's weight down, there's always weight down. There's the buoyant force due to this water. There's the buoyant force due to this water. Okay, and then someone might hang in there with this next thing. Someone might say, well, wait a minute. Okay, this is exposed to the atmosphere, so there would be atmospheric pressure down here below. Okay, but the buoyant force equation actually takes into account the difference in the fact that atmospheric pressure creates a large pressure down here relative to that. That wasn't crystal clear, but this will be good enough for right now to go through it. Okay, so if it's floating, what's got to be true? It's got to be true that these two forces exactly balance. So we ought to be able to write an equation. And let me write something up there that hopefully you can criticize and say, look, we got to fix this up a little bit. So I'm going to say like the up is equal to the down. I'm going to write an equation that says that the up is equal to down. So the up would be, our equation for buoyant force is rho Vg, okay? And the down would be the equation for, would be rho Vg as well, okay? And That is a good first step, but it's pretty deceptive. It doesn't seem like it's very helpful. So let's go through it really quickly and make sure we're clear about what these rows are. If this is the down right here, if this is the weight, this is the density of the object, which I might indicate by rho 0 or rho sub O for the object. This is the volume object, and this is G. Okay, how about over here? What about the buoyant force? This is the density of the fluid, okay? And this is the volume that's actually submerged, not the entire volume. This volume right here is the entire volume. That right there is the volume submerged. So we should maybe rewrite it and with a couple subscripts to get clear about it and see if we can finish it off. Before we do that though, hey, the G's cancel out. So that makes it a little bit easier to work with. So my next step would be on the right side, the density of the object times the volume of the object. And the left side, the density of the fluid times the volume that's submerged. Okay. All right. Well, then what we ought, I'm thinking about what we could do. Maybe what we could do with this equation is we could figure out how much actually is submerged. What is this portion over here that's below the surface level that's actually submerged? What is this portion over here like that? And obviously you can do that from the equation. So you may have another way to do it, which is just fine. But at least on your calculator or in your head, try to finish this off. If I do the algebra and solve for the volume that's submerged, I'm going to move this density of the fluid over here like this, and I could actually write it in a way that makes the computation easy by doing the ratio of the densities times the volume of the object. All right, so I'd like you to pull out your calculator and plug and chug and see if you can work that out. Okay, so just carrying it through really quickly, the density of the fluid, water, you can use 999 or 1,000. I'm going to use 1,000 in this case. The density of water does vary with its temperature and with pressure, but if we're doing approximate calculations, unless otherwise stated, we can use 1,000. The density of the object was 720. Okay, that was given up here like that. All right, and then these are both kilograms per meter cubed, so those units drop out, which is very, very nice. How about the volume of the object? That was a cube. And a cube's volume you get by just taking the side and cube it. So the volume is 1 meter cubed. So the math is pretty easy. 720 divided by 1,000 times 1, and I get 0.72 meters cubed submerged. Okay. And the math worked out very easy in this case. Let's go ahead and finish it off. What height of cube is above water? Okay, well, dividing it up, okay, we have, if we took that cube and divided it up, we have 0.72 meters cubed below water, or at the water level or below, 0.72. Okay, that's the portion that's below. So the portion above would be the difference between that and 1. My drawing sizes aren't very accurate, but that would be 0.28 meters cubed. Okay, and it is a cube, so this, we basically imagine we have a top here that's by a meter by a meter, so that's a meter by a meter. So this length right here would have to be 0.28 meters or 28 centimeters. So 28 centimeters would actually be submerged. Okay, good. So look, it's kind of like on the buoyant force, it's kind of like there's 2 levels of problems. The first level of problem is just using that equation that I have, or expression that I have on the board, to do rho VG for an object that's in a fluid and calculate the buoyant force. Boom, just calculating the buoyant force. But there's some other more challenging problems where you're supposed to work with the buoyant force and also do a free body diagram to work some stuff out. And so both those types of ideas are encapsulated in homework number 2. And I realized, hey, this class goes really, really fast. Hopefully you are done with homework number 1. I've posted solutions with homework number 1, and you're working your way through homework number 2 and get to that stuff as soon as possible. So that's the end of the first thing I wanted to do today, was finish off buoyancy. Any quick questions while we're transitioning, while I'm erasing the board? Please fire away. Okay, we're good to go. Well, let's go ahead and start the next topic then. A little bit more on delta P equals rho GH. Delta P equals rho GH. And probably the number one application we do that is manometers. So we got a good start on that last time. Just want to do a little bit more work on that. So let's go ahead and get going. So this next topic is manometers. And manometers is really the application. Instead, what we're really doing is taking a look at P is equal to PO plus rho GH, or conversely, or similarly, delta P equals rho GH, and trying to do some problem solving. Okay. If you could bear with me for just a second, I'm going to get a figure in the book up on the board. If you have the book, you could just save yourself some writing by going to page 53 in the textbook. So bear with me for just a second while I get a picture. It's not going to be good as the picture in the book, but I want to illustrate something that that book actually does. So hang in there for a second. Okay, thanks for your patience. So what I said last time, just really quickly, when I said about manometry and doing these problems with fluid statics, so this is fluids at rest, is that really what we can try to do with a problem is try to identify pressures that we know, okay, and then work our way up or down by doing rho GH, and keeping in mind that if we have a level within a fluid, okay, a level within a fluid, a uniform fluid, the pressure at any level is going to be the constant. So the pressure here and the pressure here would be constant. And that usually allows us to take a look at a diagram, identify pressures, and get to the point where we can write an equation that allows us to solve for whatever we want to do. Okay, that is basically the same as what the book says, but the book puts it slightly differently. So I just want to take a look and read what they say and go through an example that way. Many students might find the book's almost like equation type approach more helpful than the approach where you take your diagram and write some pressures. So hang in there while I get that the page 53 from the book up, and we'll start working on that. Okay, so on page 53 of your textbook, they have a section where they try to almost program you and say, hey, look, if you do the problems this way, you're going to be able to work it out. And let me read it out really quickly. They say this process, solving manometer problems, can be codified into a simple manometer rule. And they say basically, look, they say write the pressure at either end of the manometer. So I'm going to go back to the board here. So you could write the pressure, say, at this point right here or that point right there. You could call that either end of the manometer. Proceed through the manometer. That means from your starting point, go through the manometer. Add rho GH or gamma H if you go down. Okay. Subtract rho GH or gamma H if you actually move up. Okay. And then stop at the far end or any point in between and set the expression equal to the local pressure. Hey, with a little bit of work, actually, that makes some sense. So I want to go through that with you guys and see if we can label the various points on there. Okay, so what they do in the problem in the book, if you want to look at it, they start at A and work their way like that, okay? Let's just say that we have two different fluids here. This is a fluid that's in a container. Okay, this is a second fluid, and then, well, hopefully you know what's going on up over here. So let's just for argument's sake, let's just say that this fluid right here has density gamma sub g, gamma sub g. So gamma is its specific weight, actually, and this one, g, I'm saying for the green fluid, and here I'm going to call this gamma sub r. Okay, so what I'm going to try to do on that diagram, and I encourage you to do it, is first of all write some pressures, and then see if we can come up with an equation that would allow us to get the pressure at A. Before we get going, hey, let's just think about the pressure at A. Is it large or is it small? Okay, well, hopefully you remember that ordinarily, if you eliminate the red stuff, if you just had a fluid like this, the green should be at the same level. It should just form a U at the same level. Well, how about A then? Is A's pressure high or low, actually? Well, it's pushing this green down and pushing this green over here up, so A's pressure should be high. All right, let's get going. Let's just go ahead and start at this end of the manometer and write an expression for the pressure. I'll do it in just a second, but I'd like you guys to think your way through it a little bit.
You're saying
okay, here's what the book is going to write, and I encourage you to do as well. You could write 14.7 there for atmospheric pressure, or you could write 101.3. But this surface right here is exposed to the atmosphere. Sometimes in some books, they'll put a little triangle there to say it's exposed to the atmosphere. And one idea we have is at the surface of a liquid, that is at a surface, the pressure at the surface is equal to the pressure of that fluid it's exposed to. So that's going to be P ATM. Okay, we're going to work our way down. I forgot to include a couple figures in there, so please bear with me for just a second. We're going to put a line like this and a line like this, and we're going to call this H2. Okay, and then in addition, we are going to put a line like this and call this distance here H1. Okay, so the next step to do it is I would like us to get an expression for that pressure right there like that. Okay, and just while you guys are working, again, what we're gonna do is we're gonna start at one end, and if we go down, add rho GH or gamma H, and if we go up, subtract. Okay, well, this point is lower than that point, so its pressure should be higher. This point's pressure should be higher, and what we can do is just add rho GH. That is our governing equation. Okay, or we can say the pressure at this point is the pressure at the surface, or the point that we know, plus how far we descend multiplied by rho G. Gamma is equal to rho G, so what we're looking for right here is to say that this is PATM plus gamma H. And which gamma? Well, it is the gamma of this green fluid, so it would be gamma G. Okay, we're working our way back here. Why don't we go ahead and do this point right here? What's its pressure right there like that? Okay, well, hopefully as you read the problems in the book, or I'll do a good job on Thursday of indicating, it's either going to be crystal clear or actually explicitly stated that we have a level right here like that those 2 points are level, okay? So that's that idea that if we're within a U that's uniform, we're basically at the same level here and here, so the pressure should be the same. So over here, it's just to be P atmosphere plus gamma G times H. That should be that pressure there like that. Okay, 1 point to go. Why don't we go ahead and get the pressure right here like this? All right, so this is going to be, now we're going up. So we would subtract some pressure. So we would take this pressure right here and subtract gamma times H. And by the way, I have a mistake up here, I'm sorry. I should get my subscripts. This distance was H2. So this would be H2. So this would be P atmosphere, okay, minus plus gamma G times H. That was what I just wrote was the pressure right there. And then now I'm going to ascend by a height H1. And it doesn't matter that we make a 90-degree turn because we're staying at the same level. So you could say, well, the pressure here would be the pressure, I'm just P atmosphere plus gamma GH minus gamma, pardon me, goodness, minus gamma R H1. And then we're going over to the left here and it's the same. So minus gamma R H1. Okay. All right. Look, you don't need to do this on your homework. You don't need to do this on a problem on a test, but you need to be able to think this way. So trying to ignore everything on the board or all this scribbling on the board, what if our goal was actually to write an equation that would allow us to figure out PA, write an equation to figure out, hey, what is the pressure in this vessel right here like this? Okay, well, what we could do then is we could say, look, we know this pressure right here. We worked our way backwards and PA is equal to this expression. So there would be our equation. PA is equal to the atmospheric pressure minus gamma G times H2, pardon me, plus gamma G times H2 minus gamma R times H1. And that would be our equation. Okay. Hopefully, eventually what you're going to just do is, in a problem like this, is just say, oh, I can start here, and then I decrease by that much, and then I increase by a certain amount, pardon me, I decrease by a certain amount, and then I increase by a certain amount, and get to that equation on your own. Okay, that is the way I did it on the board, though, is the way the book does it. And if you look at the solutions manual, which I'll be posting for homework number 2, you'll see that way. Okay, good. Let's go ahead and do an example, actually, where getting a little bit more practice on that. Okay, so a quick example. All right, so in this example, we got a tank. Okay, and in the tank is a gas. I haven't specified what the gas is, okay? And what we want to do is we want to figure out the pressure that this gauge here reads. Tank. What pressure is that gauge going to read, actually? Okay. Obviously, you know, in reality, if that was something that you practically wanted to do, you would fit that tank with some sort of pressure gauge and it would read it for you. Okay. But historically, you know, a lot of times actually these sort of U-tubes were actually used, and they're still in use a lot of times because they can get what's called differential pressure. Wow, I don't know if you can see, I still have a little bit of olive oil in there from something I did earlier. So it's just a little bit of separation there with olive oil above the water. The blue fluid is just water with a little food dye in it. Okay, but there are situations where actually U-tubes are actually hooked up like this to tanks, and they can be used to read the pressure in the tank. It certainly is a doable thing. I'm sorry, my arm's in the way. And there are physical situations where these U-tubes are still used. We'll do an example where we're trying to get the pressure in the tank using the U-tube. Okay, so let's get that up there. So here's this U-tube. Okay, and hopefully you can think about what would be happening with the fluid level if we had some fluid in here in this U-tube and it was pushed down over here. That would mean we'd have high pressure in the tank. What if you saw something like this? What's that pressure in the tank going to be like? Is this pressure in this tank going to be high or low? Well, hopefully your intuition's locked in on that already, but let's just go ahead and do the problem solving. So let's just imagine that we used a pretty dense fluid 10 times the density of water, okay? 10 times the density of water. So its density is 19.4 slugs per foot cubed. Okay. And then in addition, I could give you the H's on the manometer, but let's go ahead and do it the way that it sometimes is expressed in good problems, like a problem like you might see on the FE exam. So let me write that out there. Manometer, differential reading. So that says manometer differential equals 6 inches. Okay. So hey, let me just go ahead and stop and get you guys going. What's that pressure gauge going to read? And let's do it in PSI. Good problem, okay? Good problem, good practice for Thursday.
Would you still work your way backwards as you did on the last example problem?
Yeah, okay, very good. That's what I would encourage you to do. And if you feel like you understand what that means and want to get going, that's fine. But I'm going to do a little bit to help, okay? So what we would like to do is think, okay, are there any pressures we know in this picture, and can we work our way up, down, left, right, and get an equation for what we're looking for? So we're looking for, actually, let me get a different color. Bear with me a second. We're looking for the pressure in this container right there like that. I mean, strictly speaking, if we're taking the pressure of the gauge would be the pressure right there at the top of the tank. And so, wow, it may look in this picture like this is a very complicated problem. But if you remember last time we worked on this principle that in gases, as you go up or down, the pressure difference is insignificant as long as we don't have huge heights. So if we have a height like even 2 meters or 4 meters or 15 feet like a tank, the difference in pressure at the top or the bottom is about the same. Okay, are there any pressures we know? We know this pressure right here like that. We know that pressure there like that. Okay, why do we know that? This symbol right here, it's not super clear because my drawings, you can't see it, but that symbol right there at the top of the tube would indicate it's open, and that would mean that there's atmosphere in here. So that surface is exposed to the atmosphere. Okay, can we work our way over to the tank? Okay, well, what I could do is I could draw a level right here like this, and then I know that pressure right there. Okay, now I could go from here to here, and that's going up. Okay, and that's where the 6 inches comes in. This phrase right here, the manometer differential, means the difference in height between one side of the manometer and the other side of the manometer. So that manometer differential is 6 inches. Okay, so we could write an expression for this pressure right here, and that pressure would be equal to the pressure in the tank. So that's our steps. We want to have a pressure here, and write an expression for the pressure there, and take it from there. Okay, I'm going to let you guys work for a second, and I'll be putting some writing on the board that's not necessary, but hopefully you can make some progress on it. Okay, there's the work right there. This is the atmospheric pressure. This is atmospheric pressure. Now I'm going up, so I'm going to subtract rho GH. And so there's basically the equation that I want to work through and solve. This pressure right here would be the same as the pressure of the gas. So I'm going to get a number up there and see if I agree with you guys. Okay, so as someone was asking last time, hey, how about dealing with all this mess of units? There is a table in the back of the book that you can use to do conversions. That's okay with me, but I really hope you can work this summer on trying to go back and forth between units like pressure units, pound units, and units with slugs. And a key thing to remember is that a slug foot per second squared is a pound. So that's a pound. This is a foot. That's a foot cubed. All this is a pound per foot squared. So before I take these two terms, atmospheric pressure and then the differential pressure 312, I need to divide by 140, that 312 by 144, and to make it into pounds per inch squared. So 312 divided by 144, I've got 2.17, or I'm going to call it 2.2. So this is going to be 14.7 minus 2.2. Okay, and I've got 12.53, or I'll just call it 12.5 for right now. Just going to 1. Okay, hey, that's not the answer. So there's one more step to do. Okay. Hey, what was this pressure right here? Is it absolute or gauge pressure? Okay, well, for the atmospheric pressure, I filled in the actual atmospheric pressure, absolute pressure, 14.7. So as a consequence, this pressure right here is an absolute pressure. So the pressure of the gas, its absolute pressure is 12.5. But this is a gauge up here like this. That's a gauge up there at the top. So we're going to turn it into gauge pressure. Remember, our idea is that absolute pressure, our equation is absolute pressure is equal to gauge plus atmospheric. Conversely, gauge is going to be absolute pressure minus atmospheric. Okay. Gauge pressure is basically how much we are above atmospheric pressure. We're actually below atmospheric pressure. So our answer would be that gauge up there would read negative 2.2 psi. And there are gauges actually that go into the negative so they can keep track of cases where pressures are really low. Okay, so good examples, maybe similar, not exactly, but some thinking like that I'm going to ask you guys to do on Thursday. And of course, homework number 2 involves some thinking like that. So before we move on to the next topic, are there any questions about this example?
I do. Where do you get the height from?
Okay, so if you take a look over here, it's a little bit different than what we've done before. Okay, what we've done before is actually that height was given in the drawing a lot of times, or expressed in the problem. The height is 7 inches, or the height is 2 meters. I would like you, but will not require you to know what is meant by this. Okay, this phrase that the manometer differential, if you ever see that phrase, that means the difference in height between the two sides of the manometer. So it says the manometer differential is 6 inches. So that means the difference between this and this is 6 inches. All right, good. All right, so take a quick mental break for a few seconds while I erase the board, and we'll do one more topic, and then we'll take that practice quiz. Okay, so next topic, a little bit about barometers. Barometers are, a device for actually measuring atmospheric pressure. And there are a lot of different types out there, but we want you to be able to familiar with the most basic type that was invented. To get going at it, I'd like to put a drawing up on the board, and I don't want you to copy it down. I don't want you to copy it down. I just want you to think about it. Hey, with that set up last, just thinking about that for a second. So here's what I got. This is supposed to be a cross section of like a dish, and there's some water in it. And this is like a straw that's put in there, okay? And the straw is open at the top, okay? Would that last? Or if not, what would happen? Okay. And the answer that is what's gonna happen actually is clearly you got this column of water here. It's gonna push down and it's gonna rush down, it's gonna lower down there, and then the water over here is gonna rise. Maybe if it might be a little bit helpful to visualize if I made this dish a little bit deeper. So if somehow you got a point where you had water like this, the water in here is going to fall until that level rises, until it equilibrates. So a little bit later on, you'll see water there like that and water going across. Okay. If we change the situation though, we seal the top. Okay. And if we ended up having a low pressure in here like this, okay, a really low pressure gas, okay, then we might have a chance of this actually working, okay? Then we might actually have a chance of this working. So let's just go through it. And again, you don't need to copy this down, just trying to build up your intuition. Let's go through it and think about what the pressures are like, okay? That dot right there, be the same as the gas pressure because this surface is exposed to that gas. How about there, higher or lower pressure? Okay, well, we've descended from this point right here, we've descended in a fluid, so that pressure is actually going to be higher. Okay, how about out here? Okay, well, I intended to put this dot at the same level as that dot, so these two pressures actually should be the same. Okay, then in addition, we might be able to come up with a number for this pressure. This water here is exposed to the atmosphere. So right here we would be at P atmosphere. Okay. This could work if this pressure were low enough. Basically, if we tried to go through and write an equation, okay, if I made this height H, okay, if I tried to write an equation for this scenario, I could write an equation that equates the pressure here and the pressure here. Pressure here, left, P atmosphere. Pressure at the right here, okay, if I called this low pressure gas P sub gas, I could say it's P gas plus rho GH, okay? And this equation would reflect the reasoning that we just did, and it also reflects the idea that the atmosphere is larger in pressure than the gas. And so the push of the atmosphere, the way it's often thought about is that the push of the atmosphere is able to hold up this column right here like this. The atmosphere is able to hold up this column, okay? What if for some reason we had a day that was really high pressure? Well, when we think about air pressure out there or air pressure in this room, like right in front of me, hey, it's about 14.7 PSI, but that pressure fluctuates up and down some. That's why we get wind. Sometimes in some parts of, say, California, over here we have a high pressure area, and over here we have a low pressure area. Fluids are always forced from high pressure to low pressure. We end up getting wind. Even though these pressures might be very, very minute in difference, like this might be 4.71 PSI, and this might be 14.695 PSI. Okay, hardly any difference in pressure between those 2 points, it turns out it's enough to have some pretty profound effects. So historically, people were very, very interested in measuring atmospheric pressure. And they got the idea that you could create a setup like this, where you had a low pressure gas in a tube, and then you had a dish. And as the atmospheric pressure increased, there would be more of a push here, and it could actually end up holding more fluid according to and this equation actually could be used to go through and solve for the atmospheric pressure. Hey, that was pretty long-winded. Let's go ahead and get going and get through an example where we work through that with a barometer. Okay. So barometers, again, an inverted tube sitting in a plate of fluid, the simplest barometers, okay, and you end up getting fluid going up the tube if we have low pressure at the top of the tube. All right, so a quick example on that. So we're going to go ahead and draw our plate, or our dish, pardon me. So there's our dish, okay. There's some sort of fluid in that dish. Here's our inverted tube, but it's sealed at the top. There's low pressure in there. Okay. By the way, in the development of barometers, one thing was really key was the development of the vacuum pump, which would allow someone actually to pull pressure out of the top of this tube. There would be a little connection up here where someone could connect a pump and pull it out. So let's say though, actually we have something worked out where we get down to 2.7 PSI. So 12 PSI below atmospheric pressure. Why don't you go ahead and see if you could write an equation and get that H. Okay, and if you're not sure about how to do it, some of you may just jump in and say, oh, I see it right away. Basically, what we're going to try to do is write an equation that relates the pressures at those 2 points. Okay, it's a little bit of work time. Oh, I'm sorry. One thing I should have said, I think I said that this is water, but you do need to know that. What is this fluid? So we're going to make it water. Okay, I'm going to start working on the board. Keep going if you know what you're doing. Okay, I'm going down. I can start at this point right here, and I can relate these two pressures to try to get a equation. Why relate this pressure here and this pressure here? I know both those pressures, and so thinking about any pressures that we know are helpful. Okay, so I could start here, and it's 2.7 psi, and then I increase by rho gh, and that's going to be the same as that pressure there. Why? They're at the same level. They're at the same level. So these two pressures are the same. So basically I could say P out this pressure here, 2.7 psi, plus as I go down rho gh, sorry about my writing, is equal to this pressure right here, which is 14.7 psi. So 14.7 psi. And that's an equation that allows me to solve for H. So I just looked at the situation and worked my way up, down, left, right, and tried to write an equation. So let me just finish it off really quickly and see if I match what you guys get. You should get a really, really large number for H if you did it correctly. hopefully a very large number for H. I believe it's going to be over 20 feet. Okay, as there are many ways you could get through it. What I did was I did the algebra first and I solved for H. I moved the 2.7 over, so I got 12. That's pounds per inch squared. And then I divided by rho G. Sometimes it's more convenient to use the specific weight instead of rho G. In this case, it is. The specific weight of water is 62.4. Okay, here I've got pounds and pounds, so that's really good. Those pounds are going to cancel out. Okay, but I have inches squared and feet cubed, so I need to do a conversion there. And I converted the inch squared to feet. Why did I go that direction? Because it probably makes sense to get my answer in feet. You could have done it the other way as well. So if I do that, I'm getting rid of the inches squared. And now I have foot cubed here, foot squared there. This is in the denominator, so this foot cubed in the denominator goes into the numerator. This is in the denominator, foot squared, so I end up with feet. Okay, and I don't know, hopefully that turned out to be 20. That's the way it's supposed to turn out. Let me just crank through it on my calculator. Okay, yeah, I got 27.7 feet. 27.7 feet. Okay, and that's the answer actually. So first of all, the math is correct. Secondly, you can see that this setup right here, that's a really impractical barometer for measuring atmospheric pressure. The atmosphere, actually, if I could get this number down to nearly zero, and there are vacuum pumps that can basically evacuate that area at the top, we can get the water to rise almost 30 feet. And the way it's expressed sometimes is the atmosphere is able to support nearly 30 feet of water. So if you wanted to make a barometer actually that would give you a good feel for what atmospheric pressure is at some point, water's a poor choice because the atmosphere can support a really tall column of water. So a lot of practical barometers instead were made with mercury. Mercury is a lot dense, and then this column ends up not being as high. Okay, good. Hey, one more thing and then we'll take a break on barometers. Great. So let me just, the last thing is a lot of times barometers, the pressure that we get from barometer is expressed in terms of height, and we want to be able to do that really well. Okay. So I'm just going to get at that by doing a quick example and have you guys go through and do a quick calculation. But I'll just write the phrase up there so you know that it's something you're supposed to be responsible for. Okay, so something that we're supposed to be able to do is, as engineers, when working with pressure, is we're supposed to be able to express the atmospheric pressure in terms of height of barometer fluid. So if we had the barometer and it was exposed to the atmosphere, how high would that fluid rise in the barometer? So that may seem very, very intimidating, but let's just go ahead and go through an example really quickly. Okay, so there's our situation. High pressure day, low pressure day. That is a really high pressure day. Usually the atmosphere is 101.3 kPa. For some reason, the air pressure out there is unusually high. Okay. And there's our problem. Okay. Hey, this is going to look really intimidating first time through. But if you understand what it's saying, it's very, very simple. They're saying, hey, what if you put a barometer in outside or in a room with this atmosphere? How high would the barometer fluid rise if the barometer fluid was mercury? And there's one more thing to add to it. We're going to assume that it's a great barometer so that at the top of that tube, we basically get down to a vacuum. Let's draw it. So I got this dish right here. This is my barometer. I invert a tube in there, and the tube's not open at the top. Tube's not open at the top. The tube would normally be very thin compared to the dish, okay? And what's going to happen is over here, the atmosphere is pushing down on this mercury. Mercury is not red, by the way, but I'm just using that for a minute. And so it's going to, atmosphere is going to actually be able to push it up this tube, and we're going to assume that up here, that this is a vacuum. VAC is sometimes used. Okay. Hey, what are we trying to figure out in this case? We're trying to figure out this H right here like this. Okay. And what fluid are we assuming that's in here? Well, if we're doing it in terms of height, in terms of millimeters of mercury, we're assuming that this is mercury in here like this. Okay. So see if you can write an equation that solves for H, and let's see if we can also work out the units, and that'll be the last thing before we take a break. I'm going to erase that 102,000. So I hope you didn't write that down yet. Hey, so once again, keep going if you know what you're doing. Okay, I was going to try to write an equation with an H in it. I'll try to write an equation with an H in it. Using the textbook's approach, I could start with a pressure I know. That dot right there is at 0. Okay, over here I know it's atmospheric pressure, and I can work my way from this dot to this dot right here. 0 plus rho GH, same as atmospheric pressure. So atmospheric pressure is 0 plus rho GH. And for these types of problems, it turns out it's a lot easier or the units are a lot easier if you express rho G in terms of specific weight. So I solve for H, and H would be, if I just move this over, H would be P atmosphere over the specific weight of mercury, and there's the specific weight of mercury. Up here, I could write 102, and this is something that it would be really helpful for you guys to know, is that a Pascal is a Newton per meter squared, so a kilopascal would be a kilonewton per meter squared, and that works out very nicely if you take a look at those units. It ends up canceling out. So I'm just going to go ahead and do the math really quickly on my calculator. 102 divided by 133. Okay, and I've got 0.77, pardon me, 0.767. Okay, and what units is that? That is meters. All right, still haven't answered the question. The answer was to figure out, hey, could I express this pressure in terms of millimeters of mercury? And that would be, okay, what is this height here of this barometer in millimeters of mercury? Well, a millimeter is, there are 1,000 millimeters in a meter, so our answer would be 767 millimeters of mercury. Okay. And notice that that's a lot more reasonable height. If you were to make a barometer, you'd have a lot more reasonable height in that case. Hey, something that a neat project that you might be able to do is actually make a barometer yourself. If you could get a vacuum pump and evacuate that area up there, you can get that water to rise pretty high. Okay, good. All right, let me talk about what we're going to do next really quickly. But before I do that, any quick questions?
Well, we need that equation sheet from the book for this quiz.
So here's what I'll send out an email. So I'll give you a verbal description, but you don't need to write it right down right now. Just see if I follow what I'm saying, and see if you have any questions. You get to make up your own single equation sheet. Okay, and I could publish an equation sheet for you, but I think it's really good practice for you to make up an equation sheet yourself. So what can be on there? You can have equations on there. You can have diagrams on there. You can have definitions on there. You could actually have like common unit conversions that you need to know, okay? But I don't want you to have any sample problems, okay? And so the equation sheet is going to be handwritten by you. I want everyone to make up their own equation sheet, and you can get to use that. In addition, I'm going to ask you to be able to use those 4 tables from the book. I believe it starts with 1 point. Let me check for a second, please. Hang there for a second. Yeah, 1.5, 1.6, 1.7, and 1.8. And so those are the materials you end up using on the quiz. Other questions? Okay.
So the conversion factor table can also be used?
Can you repeat that, please?
Can the conversion factor table also be used?
Yeah, so for those of you who aren't aware, in the back of the book or part of the book is a couple other key tables. This table we're going to definitely use later in the semester. It's one of the really, really key tables for mechanical engineers and fluids. But just adjacent to in the back of the book is a table 1.3 and 1.4 that gives you a bunch of conversions that allows you to go back and forth between different types of units. And you're welcome to use that. So that is allowable as well. Any other questions? Okay, well, let me talk about the quiz just a little bit. At some point on Thursday, we're going to have some lecture, and at some point on Thursday, I say, hey, let's take a break, and we're going to do about a 40-minute quiz. See where you're at on the material from the first few lectures, homework number 1, homework number 2, and actually the little bit that we're going to do on lecture after we're done with this short break. And I haven't written the quiz yet. I want to see how the following goes. Ideally, I would like to do the quiz on Canvas, okay, using Lockdown Browser and also with Zoom. And we actually got a lot of success, but not 100% success with that last semester in one class I was working with. So what I want to do right now is try it. So I'm going to go to share screen and describe what we're going to do, see if you have any questions, and then we'll give it a shot. Okay, so bear with me for just a second. Okay, so hopefully you can see that, that quick description. I don't know if you want to take any notes on it, but I'll just read through it. So you hopefully you guys have all used Lockdown Browser before. If you have not, that's okay. I did send a link yesterday for Lockdown Browser. We're going to take our 5-minute break when I'm done talking. It takes hardly any time to get Lockdown Browser. So if you haven't got Lockdown Browser, I'd like you to try it really quickly. So what you would do on your laptop or your PC or wherever, or your phone, whatever you're using right now, is you would close any open applications. Then you would go to Lockdown Browser and then go to the Canvas page for ME120, for ME120 this summer, this class we are in. Okay, if you go to the Canvas page, see, I'm on number 4 right now. If you go to the Canvas page, on the right side of the Canvas page, there will be a Zoom meeting identified for 9 a.m. on June 2nd. That is going to be the Zoom meeting for our quiz, okay? When you click on that, your mind might be saying, hey, there's no way I can go to Zoom because I'm in Lockdown Browser, which prevents me from going to other applications. And yet it seems to work. And it certainly worked for a lot of students in the past. And I want to see how it goes right now for you guys. So when you click at that link, an orange box is going to appear in your lower left-hand corner asking you to click here, or it may appear. For some students I've worked with, that orange box hasn't worked. But at the same time, in the middle of the screen, there's going to be something like use Zoom in browser. And by that, they mean Lockdown Browser, or use Zoom, or start Zoom from browser. And you can follow that link right there, okay? And you should be able to get to the Zoom meeting. That's what I want us to try. Okay, so what I'm hoping then is that when you go to that Zoom meeting, I will see you on the screen and you will see me on the screen. I'm going to go to that separate Zoom meeting myself. We'll check in, and then after we're checked in, you're going to actually have 2 tabs on your computer, one for Zoom and one for Canvas. You'll go to Canvas and you will take the practice quiz, which is in the quiz test module in Canvas, okay? So look, I know that's not crystal clear, but I'm not grading you on this. I'd just like you to give it a try. So first, going through it again quickly, go to Lockdown Browser. Get out of everything else first. Go to Lockdown Browser, then go to Canvas. Click on the Zoom meeting, which is 9 a.m. June 2nd. Okay, try to get to that Zoom meeting and you should see me and I should see you. So let me pause for just a second. Any quick questions out there?
Professor,
Yeah.
excuse me, I think because I'm using my phone,
Yeah.
the Zoom, I cannot open it from my laptop. So I have some issue. I don't know. I cannot do it. I
Okay.
tried to download it. Again, I delete it and download it again. It's same issue, but I'm using my phone right now.
So your phone won't let you get Lockdown Browser?
No, my computer. No, lockdown. I will try right now, but I mean the Zoom. I'm talking about the Zoom.
Okay.
I have an issue for the Zoom in my laptop,
Okay.
but I'm using my phone right now.
You're using your phone right now, but for
Yeah.
some reason, Zoom is not working on your laptop.
Yes.
Got it. Okay. Could you stay on while we take the 5-minute break and I'll just talk with you individually?
Yes, sure.
Great. So everyone, 5-minute break. We're going to come back here to this screen really quickly, and I'll talk again for like 1 more minute, and then we're going to get going and try the sample quiz. So 5-minute break. I will see you guys again at 9:25. And whoever I was talking to, I will be back in just 1 minute, okay?
All right.
right. Hey, thanks for your patience. Who was the the person who was having trouble with Zoom? What was your name?
My name is Fahad.
Say that again, please.
Fahad.
Okay. So let me see if I understand. Let me say something and then you respond and fix my understanding. When
Okay.
you've tried to come to any lectures at Sac State via Zoom, your laptop just won't let you do it.
Yeah, it doesn't look like they told me update it. When I update it, it doesn't. It's the same issue. I update it and I do everything, but it still have same issue.
Okay. Well, I had a student last semester do the test using her phone.
Okay.
So, have you tried to get lockdown browser on your phone?
No,
Okay. So
but
look, I don't want you to stress about the quiz right now, but maybe we could try that. Um,
but
you,
that
you can you get access to Canvas through your phone?
yes.
Yesterday, I sent out an announcement via Canvas that has the link you use to get lockdown browser on a device. So what I'd like you to do over the next, say, 10 minutes or so, is try to work with your phone and see if you can get lockdown browser on your phone.
Okay, lockdown. From
Okay.
where did you post this link?
Okay, so do you know how I send out announcements on Canvas?
Oh, you mean the email?
Yes.
Okay. There
The,
is.
the link is in one of the emails. The link is in one of the emails. So, but please note the following. This is gonna take at most about 15 minutes. So about 9:40, we're going to actually end up coming back to this meeting we're at right now, okay?
Okay.
So go ahead and work on that and we'll see if we can actually end up coming back to this meeting.
Okay. All right.
All right, and I'll check in with you in a little bit.
All right.
All right.
Excuse me, Professor.
Yeah,
I
go
don't know
for
if you need to go. So actually everything works except for lockdown for me. I downloaded it on my laptop, but it was downloaded, but when I tried to open it, my screen will just freeze and it will just say loading and it wouldn't get in. I did
Okay.
it 3 times and it would just go for hours like that.
Oh, wow.
I could use my phone, but I don't know if lockdown works with my phone, and I will look into it and try to use YouTube actually.
Okay. Well, thank you. Why don't you, would you, for the next 15 minutes, see if you get lockdown browser on your phone? And
Sure, I
then,
already downloaded it actually, but I don't know if there's a version. I downloaded the one for Mac since my phone is an iPhone, but
okay.
I will try. I will see on YouTube if there's a way to do it.
Okay. And by the way, if by any chance this just is not working, I will figure out a different plan for Thursday, but I wanted to try it out.
Thank you so much. There is actually, maybe I could get a laptop. I don't know if it's my laptop, even though I have the Windows 7, which is the minimum. But
Okay.
maybe you can write me an email to let them lend me a laptop or anything if
Okay.
nothing works.
Okay.
Thank you so much.
Yeah, no need to thank me. Okay. Hey, everyone else. Okay, what I'm going to do is I'm going to leave this meeting and I want you to leave this meeting as yourself and try to go through that process. So lockdown browser, go to Canvas, go to this 9 a.m. Zoom link, check in with me there. Okay, and then we'll take the quiz. Let's give it a shot and we'll do the best we can. Please don't stress if this doesn't work. Please note one other thing. About 9:45, we're going to come back and meet together at this link, this Zoom meeting that we're doing right now. Okay? All right, so I'm signing off right now.
It's 9:45, right?
9:45, correct.
Okay. Thank you.
Yeah, absolutely. Hey, Kyle's here. All right. Thomas is here.
I made it as well.
So my mic was muted,
Okay,
and
Thomas.
I couldn't switch it back on because the Zoom
Lockdown.
browser
Yeah,
disappeared.
yeah.
So that's why
thank
I
you.
was muted.
Yeah, so thank you. That must have been frustrating. I'm sorry about that. Thanks for your patience.
Yeah, no problem.
Okay, so we got 9 people here. We should have 16 or 17. We got 11. So we're getting there. We're going to relax for a couple more minutes. If you want to copy down this diagram on the board, we're going to do 2 last brief topics, and that'll do it for today. And this is one of them. But I'm going to check my email and see if anyone's emailing me, because I'd like us to be able to finish this off. We're up to 12. We're getting there. We're getting there. Just a second, you guys. We're almost there. Okay, let's see how many people are here. Yeah, we're just about there, so I'm going to go ahead and get going. So bear with me for just a second. Okay.
Hey, Professor.
Yes.
I wasn't able to get to the quiz, but will that quiz be posted like as for practice for Thursday?
Well, I can. Certainly what you could do. You may not have been able to get through the quiz because of what was going on with Lockdown Browser and Zoom. Maybe there was some sort of issue. But yes, if you're not in Lockdown Browser and you go to Canvas, you ought to be able to access that quiz no problem.
Okay.
It is a trivial problem, although hopefully you guys get it right. It's just a quick pressure problem. Okay.
Okay.
All right. Hey, while people are getting going, let me just talk for 1 minute and see if there's any quick input. Obviously, test security, I'm supposed to try to do what I can to make sure that we have something close to what would be like a classroom environment. And when I've done this in the past, when it has worked, it's been great. I've been able to watch students during the quiz, just working their quiz. They've been on the screen doing a quiz through Canvas. and it's felt like a pretty secure environment that makes things fair for everyone. But it seems like there's just a couple of issues still to straighten out. So my inclination is to do the following: to keep communicating on Thursday, to do something much simpler. And I'll send you an email about what that is. It may involve one of two things: maybe either just a Canvas quiz where I'm not watching you with Zoom, or maybe just a quiz via Zoom where we don't have Canvas and Lockdown Browser. Try to keep it really, really simple. But then at the same time, I'm going to ask if there are a few of you for whom getting Lockdown Browser to work with whatever, and Zoom with whatever device you have is an issue. I'm going to ask you to keep communicating with me, so by the time we get to test one, we have this worked out. For those of you that got it to work, or pardon me, let me just pause for a second. I don't want to take up a lot of time. Are there any quick comments or concerns?
Professor, can you let us know what you're gonna decide by tomorrow, because so we can have time to figure out what we're gonna do?
Okay. Yeah, I will. Yes, I will.
Thank you.
Sure. Other comments? Okay. Just a couple other quick notes, and we'll finish off the class. These last two topics are very simple things that are on homework number 2 and will be on the quiz. I will be having office hours both this afternoon and Wednesday. So if you're working through things and have questions about content or questions about the quiz on Thursday, I will send out a Zoom link for office hours tomorrow and Wednesday. Finally, I'm not going to make the quiz the very first thing on Wednesday. I think I will make it pretty early during lecture, but I won't make the quiz very first thing. So if there are some issues, we can talk about them briefly at the beginning of lecture on Thursday. Okay, all right. So last two, this next topic is just a little extension of what we did right at the beginning. And right at the beginning, we talked about fluid shear and the idea if you shear a fluid. So if I have some sort of fluid like in between my hands and hang on for just a second. Sorry, you guys. Goodness. My bottom hand remains stationary and my top hand moves to the right. The fluid, because of the no stick condition, you're going to get the top of the fluid moving to the right, the bottom of the fluid stationary, and you're going to get in between fluid motion in between the two plates or my two hands. That is old news, and I didn't describe it very clearly, but just getting some information up there. We summarized it by this type of relationship, that we're going to get a velocity gradient, which is du dy, okay? And that is going to be proportional to the shear on the fluid divided by the fluid viscosity, okay? And that arrangement, that equation can be arranged in any way. The book likes to write it this way: the shear on a fluid is equal to the fluid viscosity times du dy, okay? And then there's another definition, which is that the viscosity is equal to the shear divided by the gradient created. And I'll put that in parentheses. All of these are equivalent equations. It's not like you have 3 different equations. They're all different forms of the same thing. Okay, that's really pretty much good enough for Thursday. But in addition, I would like you at least to be able to think about the following situation, okay? What about if we had an object moving through a fluid? So imagine the green is a fluid, okay, and this object is like a submarine or something like that. It's moving that way with speed v, okay? What actually would be going on the top, okay, and the bottom with forces related to the fluid? Well, it turns out there would be both pressure forces and shear forces at the top and the bottom, okay? At the top, there would be a pressure force down. At the bottom, there'd be a pressure force down. But it also, if you think about it, there also would be shear forces. So let's just go ahead over on the right over here, okay? I'm going to draw that object. And I would like you to just start with the bottom, okay? And I'm going to add some lines in there that I wouldn't add in there, but just help you to think about it. Okay. Just intuitively, what direction would the force of the fluid, the horizontal force of the fluid on that object be as it moves to the right? So I just want you to think about it intuitively, and then we'll try to give an explanation. So I've got this object here, and it's moving to the right. What would the fluid do to the bottom? Okay, well, hopefully your intuition is that it would create a drag. There would be a drag backwards like that. And that's a force at the surface that's parallel to the surface. So that would be a shear there like that. Okay. I introduced this topic by saying, hey, let's think about Newton's third law and shear. So ignore this picture over here like this and just take a look at this picture. Hopefully, if you just look at the bottom half like that, you can see that if you take a look at this green area in here below my hand, I'm sorry about that shadow, but below my hand, okay, you can see that this is very similar to the picture we did our very first lecture. I have a fluid and I have a plate above that fluid, and the plate is moving to the right. There's a no slip condition, so the plate is going to pull the fluid to the right. Please don't write this down, but I'm just going to put this symbol up here. And let's just think of, here's what I'm thinking about this. I'm thinking that there's a force of the bottom on the object of the fluid to the right. Okay, and then let's just remind you what Newton's third law is. Newton's third law, in like the 6th grade form, is for every action, there's an equal and opposite reaction. Another way of saying that is for every force that we have of one object on another, there's an equal and opposite force paired with that. So if there's a force of the block on the fluid to the right, there must be a force of the fluid on the block. By Newton's third law, what direction does that need to be? That's going to be back there like that. So what we have on the bottom right here is we have the block pulling the fluid to the right, and we have the fluid dragging backwards on the block. And that is reflected by this shear here like that. That is basically sometimes called drag shear. Okay, what if we needed to come up with a number for that shear? And that's the last part of this, so I just want you to think about that. Well, if we knew information over here like this, we could isolate on this particular version and come up with what that shear would be. Okay, and that shear would be equal to the viscosity of the fluid times du dy. Okay, where du dy would be how fast this fluid at the top is moving relative to the fluid at the bottom. Okay, and we can actually figure out this term right here by thinking about what's going on. This fluid at the bottom is stationary. This fluid at the top, how fast is this moving? This fluid up here, this layer that's right next to the block, how fast is that moving? What you need to do is think of the no slip condition. Think of the no slip condition. And that if this block was moving to the right, say with speed v, call it 10 feet per second, this top of the fluid would be moving at 10 feet per second. So if you knew the viscosity of the fluid and you have enough information to figure this out, you could figure out the shear on the bottom. Okay, I'd like you to add an arrow at the top. What about the horizontal force at the top? Okay, and it's really the same idea. As this object moves to the right, it takes this fluid right here and it pulls the fluid right adjacent to it to the right as well. So there's a force of the block on the fluid to the right. Okay, well, conversely, then there would be a force of the fluid on the block backwards. That's Newton's third law. So there would also be a drag force right like that. That is a force that is tangential to the surface. So there would be a shear here as well. So in a case like this, actually, we can apply this equation, tau equals mu du dy. We can apply it both to fluids and we can apply it to surfaces because of Newton's third law. So look, there is a problem on homework number 2 that involves a block that's descending through a fluid, and you're supposed to use that reasoning. I would like you to give it your best shot on that, but that will be, if there's something like that on quiz 2, it'll only be worth a very, very minor percentage. Give it your best shot, don't stress about it. This last thing, though, is going to be worth a couple points on the quiz, and if you understand it, it's going to be points. It's going to be really good as far as like getting some free points essentially on the quiz. So let's do this last topic, and that will do it for today. All right. Okay, so bear with me while I erase the board. I'm going to put 3 drawings up there, and I don't want you to write them down. Okay. But the topic you might want to write down because it's a great way of thinking about it, at least in my estimation. Okay, 3 diagrams, no need to write them down. Okay. So look, there's going to be some situations that we're going to work if you end up going in fluids, we're going to take a fluid from one point to another. And one question you're going to want to ask yourself is, hey, could I solve this in the simplest way possible? And the simplest way possible oftentimes is to use conservation of energy. So talking about that really quickly, conservation of energy, what I mean by that. If you go back to your basic physics, you did problems with pendulums where like a pendulum ball moved from a high spot to a low spot. And you could go from one point to another and figure out various parameters like, given it starts at this point here, how fast is it going at the bottom, et cetera, and doing work like that. And we would use conservation of energy where we would say the energy at the beginning and the energy at the end are equal. And that would be simple conservation of energy. Let me put that on the whiteboard real quickly, just as a quick reminder. You don't need to write it down. So you've had cases, you know, this is something that you've done a lot in your basic physics, where you have a pendulum, okay, and you have a ball right here that's on the pendulum right here, and it swings down. And the question might be, hey, what is this velocity at this point right here? So I could call this point A, and I could call this point B. And the way we did this is we basically wrote an equation that said this. There's a bunch of different ways to do it, but please don't write this down, just a quick reminder. Sorry about my writing. Okay. We could say, look, there's some sort of, in going from this point right here to this point right here, we have a conversion from potential energy to kinetic energy. And we can write an equation that says basically like the energy we have at this point and the energy we have at that point are equal. The sum of the kinetic and the potential. And this is something very basic that you did in physics, that it turns out it's a great problem solving tool. It doesn't always apply. It turns out that then we can do something very similar in fluids with one adjustment. So going through 3 cases that you don't need to write down. This might be a tank of water, and this might be piping that takes water from here down here like this. And we might be interested, say, hey, can we work out what the speed of the fluid is as it comes down to this point and it exits? Same thing over here. This might be like a fire hose with a nozzle here like this. And we have this fluid moving here like this, and we're wondering when it goes through this nozzle, what is the speed as it comes out here like this? Conversely, this is called a diffuser, something that spreads out the fluid. And if we know the speed here, could we get the speed here like that? Okay. Well, it turns out that we can do something very similar, but the numbers work out kind of strangely, and so there's an adjustment that needs to be made. I'll try to be very brief, okay? It turns out, let me put some numbers up here like this, on this case. If this were piping of constant diameter, so let's imagine that like it's 2-inch piping over there like that, okay? If I had a speed here of something like 10 feet per second, just think about it for a second. What speed would you probably read down below? Okay. Our basic physics tells us, well, look, as the fluid moves down like this, it loses potential energy. In ordinary and basic physics, we would get a much larger speed there. It turns out, though, that if this pipe is constant diameter, the speed we get at the bottom is 10 feet per second. Okay, and that could be pretty perplexing. What would actually be going on in this case? Here's why it's perplexing at first. Okay, we would say, if we think about energy, we would say in descending, the fluid lost energy. Okay, and ordinarily we would think it would go to kinetic energy, but there's no increase in kinetic energy. So it seems like we've lost energy. And it's possible that we haven't lost any energy. What a really fundamental discovery, and I believe it was done by a physicist named Bernoulli, is that what's actually happening as this fluid descends, it's losing potential energy, but it's gaining what could be called pressure energy. And he tested that theory out, and it turned out to be true and very useful for problem solving. So when we do simple conservation of energy for fluids, it turns out we're going to have three types of energy. We're going to have kinetic energy. I don't know if you can see that up there. Let me get that up there. We're going to have kinetic energy. Okay. We're going to have potential energy. And finally, what we're going to have what's called pressure energy. All right. So we need to come up with expressions for those terms for fluids. And that's the last thing we're going to try to do, is get clear on how we're going to actually express those. And there's a variety. We're just going to do one today, and that'll be good enough. Okay, so this actually is worth writing down, or at least concentrating on, so that you have this information. So let's imagine that we got a pipe. Okay, and we have some fluid flowing right here. In that pipe, okay, we know how high that pipe is relative to some sort of level that we're going to call the zero level. Your book for that height is going to use Z. Okay, and let's say we know the speed of the fluid. Okay, and finally, let's say we have a pressure gauge right there. Is there a way we could come up with an expression for these three forms of energy? Okay, well, let me take you through the reasoning really quickly. Let's start with kinetic. Start with the kinetic energy term. No need to write it down, but see if you can remind yourself, what is kinetic? How do we express kinetic energy? Okay, and if you wrote this, okay, you're on the right track, but I hope you didn't write that down, or at least you thought that, pardon me. You're on the right track. There is a problem with using that expression, okay? And the problem is the mass term. Okay? I've got some fluid here, and what are we going to use for mass? It's a continuous flow of fluid going past this point. If I consider this point A here and this point B right there, there is continually mass going through there. And so what people came up with is the idea that we could get the kinetic energy per unit mass, and that's how we're going to do our energy term, energy per unit mass. So our expression for kinetic energy is going to be, and I'd just like you to write that down for now, and then we'll flesh it out in a couple minutes. It's going to be V squared over 2. Okay, and I'd like you, if you want to spell this out, that would be fine. But basically, what that is going to give us is an expression of energy per unit mass. Okay, let's do pressure next, because that's the really important one. Okay. After a while in fluids, you start thinking of pressure like a form of energy. And it's really good to think of it like spring energy. Hopefully you remember that when you did some problems with springs, you had a block and you actually had it going on a plane and you had it impacting the spring like that. And as it impacted the spring, the kinetic energy went away and it got stored as elastic energy. And that could be released, actually. The spring could be released and the block could end up being shot back to the left. Okay, well, you know, remember when we talked about fluids, if you went down to a fluid at some sort of depth, there is pressure at that depth, and we can describe it as a potential force. So for example, if I put an object there like that, that fluid can exert a force there like that. And when it exerts a force, it can actually do work, and work is a transfer of energy. So we can think of pressure as like a potential to do work or potential to give things energy. Well, it turns out to get similar units, it turns out what we need to do is take pressure and divide it by fluid density, okay? And that's how we're going to characterize pressure energy in units of energy per unit mass. Okay, one to go. I know this is not crystal clear, but I think once we start doing some computation, it'll start to become a little bit clearer. Last one. We also can think of a fluid as having potential energy. So this fluid right here, we can think of it having kinetic energy because it's moving. We can think of it having pressure energy because it's under pressure, and that pressure is ability means that it can do work. And we finally can think of it having as elevation energy, which I'll write as elevation energy, or you could also write as potential energy. Okay, same thing as just a couple minutes ago. If I wanted to characterize this as elevation energy, I might do mgz. But again, there's the problem. What mass? There's continually mass going through that point. And if I want to describe the potential energy it has at that point, I can't really identify a block of mass. It turns out it's very convenient just to do it per unit mass. So divide it by m, and then you get gz. Okay, and all these are units of energy. All right, last thing on quiz, this is on homework number 2, very simple. And the last sort of quick computation that I want you to be able to do for the quiz on Thursday. One more note before we do that combination, okay? All these, if in physics, when you combine kinetic energy and potential energy, we termed it mechanical energy. It's not heat energy, it's not temperature energy, it's mechanical energy. Pressure energy is also like a form of mechanical energy. If you want to roughly describe it, you can say mechanical energy is like force energy. Okay, so basically what we could say is the mechanical energy of a fluid, and I do it as lowercase me because it's per unit mass, is equal to v squared over 2, that's the kinetic, plus gz, that's the potential, plus p over rho, that is the pressure energy. And if you look in the book, a lot of times it's written in a different order with p over rho too, okay? But I really encourage you to write that down. In this class and anything you go on to that involves fluids and energy, that computation is going to be really important. Okay, hey, we got 7 minutes left. Let's see if we can do let's see if we can do an ESI and an EE example really quickly. So I'll get the example up there, get out your calculator, and let's get going. So we're going to start with an SI example. Okay, so I got some fluid. I can think about it being in a pipe, so I'll draw a pipe, although you don't need to do that. The important thing is the data. The pressure it reads here is 50 kPa. Okay, and that's going to be gauge. I'll put a G in it. Okay. This fluid's really moving, 20 meters per second. Okay. And to make the numbers easy, let's make it at a height of 15 feet off the ground, a little bit more than 15 feet. So let's do this 5 meters. Okay. Let's go ahead and figure out the mechanical energy of the fluid. Okay. And I would like you, since this is the only really super new calculation is P over rho, I would like you to start by doing P over rho. Okay, and let's just do that calculation and see how it works out. Let's make this fluid water to make it easy. Let's make this fluid water. Okay. Hey, what pressure to use? It turns out, you'll see once we get using Bernoulli's equation, is that Bernoulli's equation, we're going to just do energy equals energy. And should we use gauge pressure or absolute pressure? It doesn't matter as long as we're consistent on both sides. Not going to get that today. I'm going to do it using absolute pressure. Actually, I'll do it using gauge pressure. So I'm going to do it. We can do it either way. I'm going to do it during gauge pressure, and I'll go ahead and get going. Okay, so there's the numbers. How do we want this to turn out? I was saying that if those three expressions that I had on the board earlier, they're all in the units of energy per unit mass. So we would like this to be turn out energy in SI is joules, mass is in kilograms. We would like this to turn out to be joules per kilogram. You are welcome to pull out your conversions, but I think if you can think about a way to get through this without using those conversion charts, that would be helpful. A Pascal is a Newton per meter cubed, Newton per meter squared. So this would be equivalent to a kilonewton per meter squared, and see if you can finish it off from there. Okay, so taking a look at this, I would like this to turn out to be joules per kilogram. It's looking pretty promising. Okay, I have kilograms here. Okay, and then I have, which is good. And then these meters squared and meters cubed will cancel out, so I'll have 1 meter. Okay, this is kilonewtons, so I could take that numerator and make it into 50,000 newtons. And then I'll get what I want, because this meter will flip up. I'll get a Newton meter, okay? And so I'll get 50,000 joules over 1,000 kilograms. And if you guys could help me with my math, I believe that turns out to be 50 joules per kilogram. Please interrupt me if you see any mistakes up there. Yeah, 50 joules per kilogram. So that is the pressure energy of this fluid right here. 2 more types of energy to do, and then we're done. There also has kinetic energy. How big is the kinetic energy? And that's going to be V squared over 2. V squared over 2. Okay. So go ahead and do that computation, and we want it to turn out to be joules per kilogram. See if you can get there yourself. And in addition, we want to do GZ and see if we can get that. Awesome. So I'll be working on the board and give you some explanation in just a minute. Okay, so I got 200, 20 squared over 2. The units are meters squared per second squared. I could pull out the conversions and try to figure out how to go from this to joules per kilogram. It turns out it's pretty easy if I can think, I could multiply by a kilogram over a kilogram, okay? A kilogram over a kilogram. And then this kilogram, I want to be part of it. I wanted a kilogram in the denominator. And here I have a kilogram meter per second squared with an additional meter. A kilogram meter per second squared is a Newton. So all this mess I have over here is equivalent to a meter Newton per kilogram. Kilogram meter per second squared is that Newton, the meter left per kilogram, that's joules per kilogram. So this answer turns out to be 200 joules per kilogram of kinetic energy. And so a note you want to make might want to make for yourself, this one it might be worth putting on your note sheet, that a meter squared per second squared is equivalent to a joule per kilogram. Equivalent to a joule per kilogram. Okay, last one to do. Okay, what about the actual potential energy that this fluid has? Fluid has ability to do work because it's elevated. Okay, and that would be the GZ term. So that we can do pretty quickly. It's going to be 5 times 9.81. That's going to be almost 50. 49.05. I'm just going to round it off to 49. And how about units? This is meters per second squared. This is meters. So the units for this are meters squared per second squared, and that's joules per kilogram itself. Okay. So there we've got it. We've got the three different energies. We've got the potential energy, the kinetic energy, and the pressure energy, and we could add those all up to get the total energy. Okay, good enough. I need to let you guys go. So let me just say three quick things, and then I'll call it good. I'll stay on if people have any questions. First of all, we won't do the quiz right at the beginning of class on Thursday, so there'll be a chance, first of all, to do one more computation like this in English units, even though it's on the homework, and I'll give you the solutions. Secondly, you'll be getting an email from me about office hours. And thirdly, you'll get an email from me about how we're going to do the quiz. I don't want to be put in a situation where people are having technical problems, where the Zoom and Canvas ends up being a struggle. So I'll try to come up with something simpler for Thursday. That is it. I'll stay for a while if anyone has any questions or comments. Thanks for your patience today, everyone. And I'm just erasing the board, so please feel free to chime in if there's anything you want to talk about.
So how many questions will the quiz be? You know, approximately?
I haven't written it yet, and so I don't really think I can answer that in a way that is helpful, to be honest. And I'm not trying to be deceptive or secretive or anything like that. But basically, maybe the following would be somewhat helpful. When I write a quiz, probably the first thing I do is I just get a sheet of paper, okay, and I go through the homeworks that we have and make a list of types of problems. It's difficult, you know, to get every single type of problem that we have on a homework on a quiz, but a lot of times I can get most of them in what I feel like is reasonable. I know that that's been a point of, I don't know what you want to say, like contention or discussion between me and students over the years, but I do feel like for students who put a significant time into the homework, that the number of problems I have is either reasonable, or if for some reason I'm a little bit long, I do adjust how I do the grading. Granted, I mean, over the years, that seems to have worked out almost universally for students. I want to be honest with you guys, last semester was a tough one, where some students saw it very differently than me. But in any case, I'm going to try to write a quiz that is going to incorporate problems from homework number 1, number 2, and I believe that most of you are going to feel like you need to move through it at a good pace. I do get feedback from students every now and then. Professor Romani, I believe you're making these quizzes too simple. I want a challenge. I want something that's going to make me think and really struggle to get this all done. Maybe some of you will be in that situation. At the same time, I do get feedback from students where some students say, look, I feel like there was not enough time. I'm going to do the best I can. But here's my recommendation to you. Please, I really encourage you not to think, look, I get an equation sheet. I'm going to have time to sit down and contemplate the problem and think about the various equations that might be possible and work my way through it gradually. I don't think it's the case the way that I write the quizzes. I try to value the ability on the very basic stuff to see what to do. Bottom line, I feel like the most helpful thing is to do as many homework problems as you can. The more homework problems you do, the faster some stuff comes. Look, so I'm not trying to be deceptive and not answer your question. I feel like that's the best I can do right now. Sorry. Other questions?
Is it possible that you could post this recorded lecture on Canvas?
I think you're asking if you could watch this lecture on Canvas. Is that correct?
Yeah, I was just wondering whether if you could post this lecture on Canvas.
Yeah, I think I'm going to be able to. It's showing me that it's recording right now, and about an hour or so from now, I believe I will get a link. So I think what I will do is in the general module on Canvas, put a Word document that has the links to the lectures that have been recorded. And I'll try to include this one. I'll stay on for a couple more minutes. Anything else? Please go ahead if you have comments.
Professor, how
Yeah.
how long is gonna be the quiz?
I think it's gonna be 40 minutes.
40 minutes? Okay.
Yeah.
Thank you.
Sure, sure. I'm still here. I'm just checking something real quick. Okay, hey, I'm going to sign off in a couple minutes. Please fire away if there's something you want to ask, though. Okay, well, I'm going to sign off. You should get me an email from me about office hours this afternoon, and also an email sometime tomorrow, hopefully in the morning, about how we're going to conduct the quiz. That is it. Thank you, everyone. Have a good rest of the day.